let's say we have this spring and I connect some mass on the spring and it's moving up and down. This is the equilibrium position. So at the maximum displacement, so that's the maximum displacement, we have zero velocity. Okay, velocity is zero, and when it's going down, it's increasing, increasing, increasing. At equilibrium, that's about equilibrium, so you have maximum velocity, and then when it's going down, at the maximum amplitude, you have again zero velocity, and at equilibrium, you have maximum velocity. So based on that, you need to draw the graph, and you also need to draw a graph for acceleration versus time. So let's see how acceleration is changing. So at equilibrium, acceleration is zero, and as it moves away from the equilibrium, let's oscillate this a little bit further. You see how the acceleration is changing. At the maximum displacement, acceleration is maximum. At equilibrium, acceleration is zero, and again at maximum displacement, acceleration is maximum, and at equilibrium, zero. Okay, so that's for the acceleration. For velocity, at equilibrium, there is maximum velocity, and it's decreasing, decreasing, decreasing. At maximum amplitude is zero, increasing, 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 maximum, decreasing, 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 zero, increasing, 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 maximum. Okay, so that's what you need to represent on the graph. So here the amplitude or the displacement is maximum. Okay, so if you consider a block with a spring, so this is equilibrium position, x equals 0, and this position is where the block is on the leftmost part. Okay, it's maximum displacement on the left part. So this is negative a, and we know that at the maximum displacement, velocity is 0. That's the velocity. And how about the acceleration? At the maximum displacement, acceleration is negative omega squared x. So acceleration depends on x. Bigger the x, greater the x, greater is the acceleration. And they are also opposite to each other. So this negative sign means a and x are opposite to each other. So when displacement is maximum, acceleration will also be maximum, but because of this negative sign, it would be positive maximum. For this negative maximum, acceleration would be positive maximum. Okay, so when the displacement is 0, that's the 0 displacement, or in equilibrium position, when the block is here at equilibrium, so that's the equilibrium. At equilibrium, you see there, that's maximum. That's decreasing, decreasing, decreasing. At equilibrium, it's maximum. So maximum velocity. And how do I know it's positive maximum, not negative maximum? Because you see, this is the leftmost part, and it's moving towards the right. Okay, so this line means it's moving towards the right. When it's moving towards the right, velocity is positive. Okay, that's what we have. That's why we have positive velocity. How about the acceleration when x is equal to 0? So that will be 0. And then for this one, maximum positive displacement. When the block is here at the maximum positive displacement, x equals a. What's the velocity? Yes, 0. And how about acceleration there at equilibrium? It will be, you have maximum x here, that means you will also have maximum a, but it would be opposite to that. It would be, if it is positive maximum, then you'll have negative maximum for the acceleration. Okay, so here at equilibrium you'll have maximum velocity, and at equilibrium you have zero acceleration. At negative maximum, velocity would be 0 and acceleration would be positive maximum. At equilibrium, velocity would be maximum. At equilibrium, acceleration would be 0. At the maximum displacement, velocity would be 0. Acceleration would also be maximum when it's maximum, but it would be down, negative. At equilibrium, velocity is maximum. Acceleration would be 0. At negative maximum, velocity would be 0, but acceleration would be also maximum, but it would be positive. Okay. So now connect those dots. So connect that, connect that. So that's the graph for velocity versus time for acceleration. So that's the acceleration versus time. Okay, it's not touching. So you see that this is just upside down of this one. So if it is going up like that, so this is going down. When it's going down like that, it's going up. So just mirror image of this one. Okay, so that's the graph. Now let's look at A. When x is greater than 0, x is greater than 0 is this part. So for this part, you see x is greater than 0, it's on the above up part. This is also part where x is greater than 0. So during this time, from here to here and from here to here, x is greater than 0, x is greater than 0. So for that part, it's asking, is a ever greater than 0 for this part? So let's go down. So during this time, from here to here, is a ever greater than 0? No. A greater than 0 means it's on this top part. You don't see any graph on the top part, right? So that means that a is no. Likewise, for part B, when x is less than 0, so which part is x less than 0? So let's see that. So this part is x less than 0. It's on the bottom, so x is less than 0. This part is also x less than 0. It's on the bottom part. So for this time duration, go down here, this time duration, it's asking, is a ever less than 0? From here to here, do you see a on this down part? No, there's no graph on this part. For this duration, there's no graph on this down part. It's all positive. It's all greater than 0. So that's also no. Can you make a general conclusion about the relationship between the sign of x and the sign of a? I already answered that. So when the displacement is negative, you see acceleration to be positive. When you see x to be positive, you see acceleration to be negative. When you see that to be negative, you see that to be positive. So you can now conclude about the sign of a and x. They are opposite to each other, right? So a and x have opposite signs. Now part D. So for x greater than 0, do you see any part that has v greater than 0? Yes or no? Yes. So this part is greater than 0. So this from here to here, see that part, velocity is greater than 0. Right? Likewise, this part, x greater than 0, for that part, from here to here, you see you have this part, where V is greater than 0. So that means yes. And how is the oscillator moving at these times? So during this time, how is the oscillator moving? Meaning, what can you say about its velocity or speed? So this going down means velocity is decreasing or it's slowing down. So during that time, it's slowing down. Now let's look at number 2. So you have this energy diagram where this line, this straight line, is showing the total energy. This line is showing total energy. This is kinetic energy plus potential energy. And this line, this blue line, is showing the potential energy. So it's not showing the kinetic energy, but we can actually see what the kinetic energy in this diagram. So if I want to see kinetic energy in this diagram, so kinetic energy is total energy minus potential energy from this equation. So the difference between total energy, this line, and this graph is the kinetic energy. For example, at this point, the difference between this line and this point is that. Okay, it's not there, it's here. So this height will give you the kinetic energy. Okay? If you want to find the kinetic energy at this point, so you will find the kinetic energy by subtracting this line, this curve from that line. So this height will give you kinetic energy at that point. This will give you kinetic energy at that point. Okay? So this length is the kinetic energy. Now let's answer the first one. So what's the spring's equilibrium length? Meaning, where is the equilibrium position? What can you say about kinetic energy at equilibrium position? Kinetic energy depends on velocity. So greater the velocity, more is the kinetic energy. So maximum velocity, that means maximum kinetic energy. You see here, maximum, that's the equilibrium position, maximum kinetic energy. So kinetic energy is maximum because V is maximum. How about potential energy? So total energy is always same. Total is always same. If kinetic is maximum, what should be potential then? It's 0 or minimum, right? So at equilibrium, it's minimum, or you can also say it's 0. So look at this graph and see where the potential energy is 0 or minimum. That's the equilibrium position. So start from here, it's going down, down, potential energy is decreasing, decreasing, decreasing. It's that point where it's minimum. Okay, so answer to A is equilibrium position, X equilibrium is 20 centimeters. Okay, so that's part A. Part B, what are the turning points of the motion? So turning points. So what happens at the turning points? So let's look at this simulation again. So that's the turning point. So it stops there and then it comes back. That's the turning point, and that's the turning point. So look at what happens to the potential energy and kinetic energy at those turning points. Yeah. So about 0 kinetic energy at that point and maximum potential energy. So you see at the turning point 0 kinetic energy but maximum potential energy. Why maximum potential energy? Because there is maximum stretch. Maximum stretch means maximum potential energy. So that's the property of turning points. So kinetic energy is 0 or minimum, and potential energy is maximum. So you see this line is kinetic energy. As it's moving to the left, it's decreasing, decreasing, and at this point kinetic energy is 0. Same thing on this side. So that's the kinetic energy difference between total and potential. That's the kinetic energy decreasing, and at this point kinetic energy is 0. And according to this property, kinetic energy, wherever the kinetic energy is 0, that's the turning point. So turning points, x turning is this, which is 14, and this one, 26. Okay, so these are the turning points. What's the particle's maximum kinetic energy? So maximum kinetic energy occurs at this point. So that's the point where you have maximum kinetic energy. And maximum kinetic energy occurs when potential energy is 0. Right? At this point, potential energy is 0. So total energy, let's just write TE. Total energy equals potential energy plus kinetic energy. And when this is maximum, this is 0. So kinetic energy maximum equals total energy. A little bit more than 6 maybe. I don't know. So maybe 6.3.